Alright, when's August 28th? Alright, let's do this. Alice and Bob playing flower games. Alice and Bob are playing a turn-based game on a field with 2 lanes of flowers between them. There are X flowers in the first lane between Alice and Bob and Y flowers in the second lane between them. The game proceeds as follows. Alice takes the first turn. In each turn, a player must choose either one of the lane and pick 1 flower from that lane, from that side. At the end of the turn, if there are no flowers left at all, the current player captures their opponent. Huh? The current player captures their opponent and then wins the game. I don't understand what that means. Like just go there and grab them? Given 2 integers, n and m, and the task is to compute the number of possible pairs that satisfy. Wait, hold on. So basically we have 2 lanes and then we saying each time you can pick one of them, right? And at the end, if there are no more, after you pick it and there is no more flower, then you win the game. So given 2 integers, I think these are the flowers. And task is to compute the number of possible pairs that satisfy the condition. Alice must win the game according to the described rules. The number of flowers in the first lane must be in the range, and the number of flowers in the second lane must be in the range. Return the number of possible pairs that satisfy. So basically we have the maximum, which is n and m, right? So we want to find an x and y such that, oh, it doesn't matter, Alice or so such that the first player wins, right? Such that the first player wins. The first player wins means, because you take one and I take one, you take one and take one. So the first, and also we don't know the 1, 2, and 2, 1 is the same, right? That's the same. But hold a second. So Alice takes the first. So isn't everybody is 1? Should work. It shouldn't be like 1, 1, 3, 1, 2, and 2, 1, and 3, 1. Shouldn't it have at least 4 of them? Oh, at the end of the turn, if there are no flowers left at all. There's no flowers left at all. So like all the flowers has to be gone. Right? So Alice picked first. And then, so it has to be an odd number. Which means this can win, this can win. These can't. And 2, 3. And actually the question is just how many different pairs can we make such that the sum is an odd. That's it. Because it doesn't matter if it's odd. Because if it's odd, then it's guaranteed that the first player will win. So how many can we do odd? So basically we say 1 and we'll find all the numbers. We have basically n and m, right? So we say we take this as a 1 and we find all of this. So basically the number of, because this is odd, it has to be even. So number of evens here, right? And it has to be starting from 1. So basically it's 2, 4 all the way. and it doesn't even have to consider, so it's just the total number of evens here, the total number. So if it's this, then it's total number of odd, right? And 3, 4, 5, 6 all the way to the end. So, and the number of hold on, let's try. Ugh, that is not what we want. So the question essentially asks, how many different pairs can we find such that the sum of the values is odd? If we have a swap, there we go, we have, so if n is larger than m, then we swap. Actually, I'm not sure. Probably should check. Oh, yep, that's the one. We can do swap. Okay. Yeah, so we make sure n is smaller than this. And then we can say a long rest. And then we need to know the count. Even count. Even count. So starting from 1, right? So it should be divided by 2. So if I'm 3, even count is 1, right? So 3 minus 1 divided by 2. Odd count. So 3 divided by 2 is 1. Oh, I think it depends on if it's even or odd. If it's even, then it's the same, just divide by 2. If it's odd, then one of them is divide by 2 plus 1. So even count shall equal to divide by 2. M divided by 2. Because it doesn't matter. If m is even, divide by 2. If m is odd, divide by 2. They always divide by 2. Odd count. Odd count should be m plus 1 divided by 2. If it's even, plus 1 divided by 2, doesn't matter. It's still the same. If it's odd, then yeah, so we got the count. Ooh, can we do long? Oh, I have a better idea. Counts. So we do even count, odd count, right? And then here I can say rest plus equal to counts I mod 2. Right, I mod 2 can be easy to do I and 1. So this will be even. If it's even, then we'll go even. If it's odd, so I should swap these two positions. I'll make it much easier. Right? So now, if this is even, probably keep this. If it's even, that will be 0. Then we add the odd count. If it's odd, then we'll go 1. Then we add the even count, and then we'll return 0. Return the result. All right, let's give this a swing. Oh, it looks to be right. Yeah, it is right. Well, we can technically do it, I think. I feel like we can do 01. Let's try. I think we can do 01 time. This is fine. We don't do this. When we do I don't even need to do that. So depends. So rest shall equal return. If n is odd or is even, okay? If it's even, then it'll be n divided by 2 multiplied by odd count, which we can do as this n plus 1 divided by 2. Oh. M even count, M odd count, N even count, N odd count. So what we do is N even count multiplied by M odd count plus N odd count multiplied by M even count. That seems to be even simpler. Okay, give this one a swing. Oh, I don't even need this one then. It's not necessary. I can remove this. Yep. Huh. We can do even better. Yeah, this is this times this. Now this times this plus this times this. So essentially what we're doing is m divided by 2 times n plus 1 divided by 2 plus n divided by 2 times m plus 1 divided by 2. So yeah, just m times n plus 1 divided by 4 plus n m plus 1 divided by 4, which is mn plus m plus mn plus n. How'd you get to this? Use some tricks there. So instead of plus 1, you can do a minus 1. I see. I see now. We cannot do better in this one. It has to be minus 1. Alright. That's alright. That's alright. Good. Now we're done with this one.